Ladies and gentlemen, welcome to our new video. Today we will talk about OT and IT in manufacturing. Okay, uh, here this section sets the scope. What is that? OT and IT inside manufacturing. Here the reason is this matters is simple. Factories run on physical actions and businesses run on data. When these stay separate, decisions arrive late. And when they connect, decisions arrive while the process still runs. Okay, now focus on the left side. What is OT? Operational technology. OT deals with equipment that moves, hits, presses, or measures. And think about controllers reading sensor values and reacting within milliseconds. Why that speed? Because a valve opening late or a motor stopping late causes real damage. That explains why availability and safety sit at the top here. And long equipment lifetimes follow naturally. Machines stay in service for decades, so change happens slowly and carefully. And information technology here shoots your eyes to the right. IT handles data after it exists. Servers store it, networks move it, applications analyze it. And timing works on seconds or minutes because nothing physical breaks if a report loads a bit later. Security prioritizes flips as a result, data protection and correctness matter more than immediate response, and systems refresh frequently because software improves quickly. Okay, and here track stack and pure model, and yes, that's okay. Let me align like that. Yes. Anyway, start at the top. Levels 5 and 4 represent enterprise and site planning. These layers answer questions like what to build, when to build it, and where inventory should go. Decisions follow downward as schedules and targets. At initial DMZ, what's that? I mean demilitarized zone. Here, these exist to control data movement. Instead of allowing free traffic between business systems and machines, traffic passes through controlled gateways. Firewalls, historians, and jam servers sit here to limit exposure while still allowing information to move forward. And their low layers continue downward. Level 3 coordinates operations, Level 2 supervises areas, Level 1 executes control logic, and Level 0 touches sensors and actuators. Each step down increases speed requirements and reduces tolerance for disruption, and that explains why IT practices cannot simply drop into these layers unchanged. And we have a table here. Look at the comparison table here. Focus on that. So each row explains a design trade-off. Response time differs because physics demands determinism. Availability targets differ because downtime at the machine stops production instantly. Security ordering differs because a stopped process creates immediate harm. And patch timing differs because restarts interrupt production. Lifespan differs because hardware depreciation runs slower than the software cycles. And failure impact and change process here you can see. And we have cards. Look at that. What's 6 cards? Okay. So what are the equipment categories? And first, PLCs here. Uh, Start with PLCs. These act as real-time execution engines. They read inputs, run logic, and write outputs in fixed cycles, so behavior stays predictable. And HMI and SCADA systems. These systems give operators visibility and control. They translate raw signals into screens, alarms, and trends so humans can intervene quickly. And robots here, I mean industrial robots. Robots extend automation into motion. They rely on precise timing and safety interlocks because they share space with people and equipment. And here, sensors, drives, and safety systems. So here, sensors convert physical conditions into signals, and drives regulate motor behavior, and safety systems override everything else when limits are crossed. Together, these form the execution core of a plant. Okay, and convergence here. Now, the message here is economic pressure. Manufacturers push for better output, lower waste, and faster response to demand. That pressure forces data to move from machines to planners without delay. And metrics here, and look at the numbers shown. Here, adoption rates, efficiency gains, downtime reduction, and market size all point in the same direction. And connecting these layers produces measurable outcomes. Okay, so here focus on the circle labeled IT, OT convergence. Each surrounding circle represents a use case fed by shared data, and real-time visibility comes from live mission data. Maintenance prediction comes from patterns over time. Quality control comes from linking parameters to outcomes. Energy control comes from monitoring consumption. Supply chain here, alignment comes from connecting schedules to production, and the digital twins come from mirroring behavior in software. And again, some cards. Look at that. Now, each one answers a specific question. What's happening now? When will something fail? Why did quality drift? Where is energy wasted? How will schedules stay aligned? How can scenarios be tested without stopping production? The common requirement across all of them is consistent, trusted data. Okay, here and some challenges. What are they? First, technical challenges. Here, protocols vary. Older equipment resists change. Timing constraints remain strict. Networks require segmentation, and data labels rarely match. Each issue forces design decisions rather than quick fixes. And organizational things. Here, teams prioritize different outcomes. Ownership blurs. Hybrid skills stays scarce. Budget follows different rules, and vendors protect closed systems. Coordination becomes a management problem as much as a technical one. And here we have security implications. So look at the security diagram on the left. Isolated OT networks relied on physical separation. Risk stayed lower because access stayed limited. Okay, and shift right once system connect exposure grows, of course, and remote access paths appear, lateral movement becomes possible, and supply chains introduce risks, and production systems become targets. This explains why layered security controls matter here. And here, risk scale bar. As connectivity increases without controls, exposure rises steadily. The takeaway is clear. Convergence delivers speed and insight when designed carefully, and it demands disciplined architecture when systems connect. Okay, and let's continue. Section 3. Patterns. Up to this point, we talked about why connection matters, and here the focus changes to how teams actually wire systems together without breaking safety, timing, or trust. These patterns exist because factors cannot accept random connectivity. Every arrow here has intent behind it. Okay, now look at that. Industrial Demilitarized Zone or IDMZ. What's happening here? This, um, DMS pattern. This is the most common starting point in real plants. Okay, and the logic is simple. Business systems and production systems never talk face to face. They always speak through a controlled middle zone. And the IT zone here, you see enterprise applications, planning systems, analytics platforms, cloud services, and remote users. And these systems move fast, update often, and expect flexible access. That expectation stays contained in this zone. Okay, and enterprise firewall now pause at the red firewall line. This firewall enforces strict direction and strict rules. Nothing passes freely. Every allowed connection is deliberate, locked, and narrow in scope. Okay, and move one layer down into industrial DMZ. So what's happening here? This zone acts like a customs checkpoint. Jump servers exist here, so remote engineers enter through a single controlled door. Historians sit here to mirror data, not to run production. OPC servers translate protocols instead of exposure controllers. Patched antivirus servers mirror updates, so machines never reach the internet directly. Orange Band industrial firewall. Between DMS and production sits another firewall, this time one that understands industrial traffic. It inspects protocol behavior, not just only ports, also protocol behavior, so commands stay predictable. And you see the production side, controllers, operator interfaces, safety controllers, and field devices live here. This zone prioritizes stable timing and consistent behavior. Any unexpected traffic becomes a risk. So, some principles, what are they? Design rules behind this. There are no direct connections between IT and OT. Data moves upward by pulling, never by pushing commands downward. Services in the middle avoid long light sessions and store credentials. And multiple layers of protection reduce dependencies on a single product or vendor. Each role exists because recovery from mistakes on the plant floor costs real time and money. And pattern 2 here, edge computing architecture. This pattern appears when raw data volume grows too large to ship upstream as is. And edge to cloud diagram is here. At the top sits the cloud platform. This area runs analytics, learning models, data storage, and applications that need scale. Okay, and notice the arrow direction here. Only processed data flows upward, and that decision saves bandwidth and reduces noise. And here, edge computing layer, edge gateways and servers sit close to machines. They collect signals, normalize tags, compute summaries, and sometimes run local inference. When something needs immediate action, it stays local. Okay, data reduction here, and look at the numbers. Tens of hundreds of tags sampled every second shrink into a few hundred indicators every minute. That reduction changes cost, latency, and reliability all at once. And field device layer, production lines, packaging areas, and utilities generate raw signals. Edge systems speak the language of controllers, then translate upward. Okay, and pattern 3, unified namespace. Okay, and here we arrive at a different way of thinking. The unified namespace pattern changes how systems connect conceptually. First, left side, publishers. Here, production systems publish data. Controllers, supervisor systems, historians, sensors, and execution systems all send messages. They do not know who consumed the data. They only publish updates. Okay, and unified namespace, center block is here, blue. That part sits a message broker cluster. Topics follow clear hierarchy such as enterprise, site, line, device, and metric. And payloads follow a consistent structure. When a device comes online or goes offline, that state appears immediately in the data stream. And subscribers, business systems subscribe. What's that? I mean, uh, planning systems, data platforms, analytic tools, dashboards, and mobile apps all read from the same stream. Adding a new consumer changes nothing upstream. Okay, and small benefit parts. The reason teams adopt this model is clarity, right? One logical data address space replaces point-to-point links. Producers and consumers stay independent. Scalability here, scale increases by adding broker capacity, and updates propagate instantly. That and shared data meaning removes vendor-specific guessing. And what are protocol standards for convergence? Look at that. Glance at the protocol standards shown. So UPC-UA handles structured industrial data securely. MQTT carries lightweight publish subscribe traffic. Modbus, TCP, and Ethernet IP remain common at controller level. And Profinet dominates many European sites. Spark Plug B defines structure on top of MQTT. REST and AMQP support enterprise integration, and each protocol fits a layer rather than replacing all others. Alright, now security, other important topic, and here connected systems require layered safeguards aligned with industrial reality. And start from the outside. Physical protection controls who enters facilities and who touches equipment. And network security here, what's happening here? One layer inward, network controls segment traffic, filter protocols, and monitor behavior. And application, moving inward, applications validate inputs and apply controlled updates. And host security closer still, systems harden operating environments, restrict execution, and monitor endpoints. And data security near the center, data protection ensures confidentiality and controlled access. And center, protect assets here. At the core sit assets that must remain stable and trusted for operations to continue. And what are they? These four things. Supporting all layers are perimeter controls, network controls, endpoint controls, and monitoring. logs, detection systems, inventories, and response processes close the loop. Okay, and what are security levels here? Now, IEC 62443 defines how much resistance a system is expected to provide against different kinds of threats. At the lowest end, security level 0, you are basically dealing with test setups or lab systems. No reproduction is assumed there. As we move to security level 1, the focus shifts to accidental mistakes. Think of someone clicking the wrong thing or misconfiguring a setting. Nothing malicious, just human error. And security level 2 raises the bar. So now the system is expected to withstand simple intentional actions like basic scripts or insider misuse. And this is where most normal production environments sit. Security level 3 assumes attackers who know what they are doing and have time and tools. At this level shows up in high value manufacturing and infrastructure. Security level 4 sits at the extreme end. This is about defending against state-backed groups with serious resources. You only see these in defense, nuclear, or nationally sensitive systems. The key idea here is proportionality. You don't design every system for the highest level. You match protection to risk. Okay, zone and conduit model. So this model answers a simple question. Where do we draw boundaries and how do we control what crosses them? On one side, you have the enterprise zone. That's where email, web access, and cloud services lie. This zone usually targets a lower security level because disruption here is painful but not physically dangerous. And moving inward, you reach the manufacturing zone. Systems like supervisory control, operator interfaces, and data historians live here. This zone typically requires a higher target because production downtime has real cost. And between these zones sits a conduit. A conduit is not a cable, it's a controlled pathway. Firewalls and data diodes live here to enforce direction and rules. And going deeper, you enter the control zone. Controllers, drives, and robots live here, and the tolerance for interference drops sharply. And you see the safety zone. Finally, this zone stays isolated by design. Emergency stops and safety controllers do not depend on network availability. And the dashed line you notice represents an air gap, meaning no digital path exists at all. The logic is simple. If everything else fails, safety still functions. And here, with that structure in mind, let's talk about day-to-day realities in operation environments. First comes visibility. You cannot protect what you cannot list. Maintaining a full inventory of controllers, interfaces, switches, and software versions matters because many sites inherit equipment over decades. Passive monitoring helps here because it observes traffic without disturbing operations. And next comes vulnerability handling. Unlike IT systems, you cannot patch controllers every week. So teams compensate using segmentation, intrusion detection, and strict control over what applications can run. Access control follows naturally, and roles matters. Engineers, operators, and vendors should not share accounts, right? And remote access needs stronger checks because distance removes physical oversight. And monitoring then ties it all together. Industrial-aware monitoring looks for abnormal protocol behavior rather than generic signatures. backups come next. And controller programs and interface configurations must exist offline. When ransomware hits, recovery speed decides whether production resumes in hours or days. And finally, response planning matters. When something goes wrong, safety and continuity come first. Isolation steps must exist that do not force a full plant shutdown. Okay, and here, last thing of the page. It is worth pausing and talking about what regularly goes wrong. Flat networks allow attackers to move sideways without resistance. Default passwords remain active longer than anyone wants to admit, and services that nobody uses stay enabled because disabling them feels risky. Shared operator accounts remove accountability, direct internet access sneaks in during troubleshooting and never gets removed. And uncontrolled USB usage introduces malware through convenience, and these problems rarely come from bad intent. They come from shortcuts taken under pressure. Okay, and let's see what's next. Oh, sorry, here implementation roadmap. I double clicked. Okay, so how does a team move from awareness to execution? And that's where the roadmap comes in. So this is a stage approach designed to reduce risk while building capability. The first stage focuses on understanding, inventory, network mapping, risk analysis, and gap identification all happen here. This stage usually takes months, and that's normal. Rushing this step creates blind spots later. Okay, and the next stage builds the base. Segmentation gets implemented, and firewalls go in, control DMZ appears, monitoring tools come online, access roles get defined, and only after that does integration begin. Data starts flowing through approved paths, edge systems appear, cloud platforms connect through control gateways. Antics finally get reliable input. The last stage never really ends. Models improve, process automate further, and scale increases where value is proven. So here Gantt chart, and when you see this laid out on a timeline, notice the overlap. Assessment does not stop the moment foundation begins. Monitoring starts early and grows over time, of course. And data connectivity, what's happening here, you know, expands gradually, and optimization, you know, stretches forward indefinitely. This pacing protects operations while still moving forward. And critical success factors, what are they? None of these works without alignment. Leadership support sets priorities, mixed teams prevent blind decisions, clear ownership avoids confusion, training reduces resistance, metrics tie effort to outcomes on the technical side. Standards create shared language. Small pilot efforts reduce risk. Early architectural decisions prevent rework. And vendor relationships stay balanced. Skill development bridges the gap between IT and plant reality. And some checklist here, you have three. At this point, the checklist simply confirms discipline. Assets documented, assets documented, networks understood, protection deployed, access defined, response planned, integration executed step by step, and remote visibility enabled with care. And here pitfalls. It helps to know what to avoid. Trying to change everything at once usually fails. Forcing office patterns onto production ignores timing constraints, and excluding plant staff leads to fragile designs. And here, underestimating older equipment causes delays. So treating protection as an add-on increases cost later, relying on one supply limits options, and skipping a business case weakens long-term support. Okay, and here we'll look at uh, use cases. And here, first, predictive maintenance. Since unexpected stops cost time, materials, and trust. So, on the plant floor, equipment produces physical signals long before failure appears. Vibration shifts slightly, temperature creeps upward, current draw changes, and pressure drifts. Sensors pick up these changes continuously. Instead of sending raw noise upstream, nearby compute handles first pass work. Features get extracted and patterns compared and early warnings formed close to the asset. When needed, selected data moves to centralized sonic systems where models improve using history from many machines. And what comes back is not raw data, but guidance. And remaining useful life here estimates turn into plant work. I mean, spare parts get scheduled and maintenance shifts from reactive to planned without interrupting production flow. And here are some cards and use case 2, and that focus on visibility during production rather than after the fact. And a line produces counts, cycle times, and state changes. Quality systems report defects and inspection results, and downtime tracking records why a line stopped and for how long. And these streams converge into a calculation engine that continuously updates effectiveness. The math stays simple but powerful. Availability times performance time quality equals OEE right here. And what matters is timing, because the calculation updates as events occur. Supervisors see trends while there is still time to act. And the display doesn't exist for reporting, it exists to change behavior during the shift. And energy management here. Energy often hides in plain sight because costs appear later on a utility bill rather than on the line itself. When consumption data gets tied to machines, products, and time windows, patterns surface quickly. Peaks align with specific processes. Inefficiencies show up during idle states, and compressed air losses become visible as constant demand with no output. And once this information is connected to controls, responses follow. Loads shift, motors adjust, ventilation responds to occupancy. Energy per unit becomes measurable rather than assumed, which fits both costing and environmental reporting. Okay, and quality traceability, it extends this same idea across the entire product lifecycle. Materials arrive with identifiers, and those identifiers follow the product through storage, processing, and assembly. Along the way, process conditions such as temperature, pressure, speed, and duration get captured automatically, and inspection results, lab data, and manual checks join the same records. And when an issue appears later, teams no longer guess. They trace backward through actual conditions and isolate affected units instead of entire batches. This capability matters most in regulated environments, where proof carries as much weight as performance. And some industry-specific applications. First, automotive plants focus on traceability and synchronized logistics to keep lines moving without excess inventory. And pharma sites rely on electronic records and environmental tracking to satisfy compliance demands. And for food producers, we can say monitor temperature and cleaning cycles to protect consumers and reduce waste. And chemical operations watch emissions and batch conditions closely. Discrete manufacturing looks for throughput gains and reduced downtime. And packaging lines target faster changeovers and inspection accuracy. The common thread is the same data foundation applied to different pressures. Okay, and I guess final page, yes. Okay, now supporting these outcomes require a layered technology stack that respects separation of concerns. At the bottom, here, what we can see, the physical infrastructures cost compute whether on-site or in cloud environments, and above that, connectivity handles communication using industrial protocols suited for controllers and devices. And the edge layer sits close to machines, handling local logic, buffering, and translation. And data platforms store time-based information at event streams. Analytic systems extract meaning, train models, and detect patterns. Okay, and applications present results through dashboards, alerts, and mobile views. And that security plans every layer rather than sitting on top because access control, monitoring, and encryption only work when designed end to end. Okay, and here some platforms. Edge gateways deserve special attention because they form the bridge between equipment and higher layers. And some platforms focus on broad automation support with built-in visualization and storage, and others specialize in protocol translation and legacy connectivity. And message brokers emphasize skill and publish subscribe patterns. And cloud-aligned run times push compute closer to machines while staying managed centrally. And vendor-specific offering integrate tightly with their automation ecosystems. The right choice depends less on features and more existing assets and operational constraints. And cloud IoT platforms look at that parts. Some excel at asset modeling and large-scale data lakes, and others align closely with enterprise tools and digital modeling. Some prioritize data science workflows and learning pipelines. Others integrate with product lifecycle systems or automation vendor stacks. And selection usually follows organizational alignment rather than technical capability alone. And final part, data architecture components. Underneath everything, data handling components keep information usable. Time-based databases store signals efficiently, and message brokers move events reliably. And each option treats simplicity, scale, and flexibility differently. The architecture works when these choices match actual needs rather than threats. Okay, and that's all for this lesson. Let me show you platforms again. And thank you for listening.